So welcome everyone to today's and the first talk of this new season of Row. It's a great honor for me to introduce today's speaker, Daniel Kuhn. So Daniel is a professor of operation research at the College of Management of Technology at EPFL. He's also the chair of risk analytics and optimization there. Of course, he's quite well known. And it's an honor having him here for his work on robust optimization and distribution robust optimization, and of course on data-driven decision making. His research is primarily application-driven, with the application being around engineering system, machine learning, business analytics, and finance. So, and he's also the editor-in-chief of a mathematical programming journal. So thanks a lot, Daniel, for being here. And without further ado, I want to give the control of the screen and the mic to you.
Thank you very much, Reza, and thanks a lot for inviting me, both to you and Yanis, and also for actually maintaining the robust optimization webinar. It's great that we have that. So big thanks to you, and thanks everyone for attending. So my talk is broadly about distribution robust optimization with Wasserstein ambiguity sets, and this is joint work with my PhD student Yves Richner, and with Adrian Esteban Perez and Juan Miguel Morales. So at the time when we started this work, they were at the University of Malaga. Now Adrian is in Rotterdam. So, in contrast to most work on optimization under uncertainty, in this talk, we will assume that the data from the true unbiased probability distribution that is relevant for our optimization problem is very scarce, or perhaps completely unavailable. And the idea is we would like to investigate whether other biased data sources could be leveraged for better decision making. Okay, so let me first recap some basics from data-driven decision making. So throughout this talk, we address a single-stage stochastic program, and such problems seek a decision theta that minimizes the expected value of some loss function L, where the expectation is evaluated with respect to some distribution P, which is the distribution of the uncertain problem parameters Xi. And throughout this talk, I would like to refer to P as the target distribution. So in practice, this target distribution is typically unknown. However, the decision maker often has access to independent training samples from P. And these can be used to construct an empirical distribution, which is just the uniform distribution on the training samples. So a popular approach to data-driven decision-making is to solve the sample average approximation problem, the SAA problem, which is obtained from the original stochastic program by simply replacing the unknown target distribution with the known empirical distribution. So then the optimal solution of the SAA problem is typically evaluated on a test set. And this, much like the training set, this test set consists of independent test samples from the target distribution, but they're different from the training samples. So then it often happens that the loss on the training data is smaller than the loss on the testing data because of overfitting effects. This means that the training loss may be a bad and in fact too optimistic predictor for the loss that the decision maker faces when implementing the solution of the SAA problem. So therefore, the difference between the test and the training loss is sometimes referred to as the post-decision disappointment. So instead of solving the SAA problem, one could alternatively solve a data-driven distributionally robust optimization problem, the DRO problem, which minimizes the worst case expected loss with respect to all distributions in some epsilon neighborhood of the empirical distribution. Now, it has been observed that this form of robustification can reduce the post-decision disappointment. Okay. So unfortunately, both SAA and DRO become ineffective when the number of training samples is small. And this is troubling because training data is often scarce or even absent in many relevant decision problems under uncertainty. For example, if a retailer would like to build a new store, in a new region, or if the retailer would like to expand into a new market, then there is simply no historical demand data to inform assortment planning. Similarly, a manufacturer launching a new product, for example, a smartwatch, and this is an example that I borrowed from Melvin. So this manufacturer has no historical sales data to predict the product's demand distribution, which would be needed to inform production planning. As a third example, an investor trading in new securities has no historical market data to predict the security's return distribution, which is in fact needed to design a portfolio strategy. So broadly speaking, one could say that whenever an organization faces structural disruptions or implements some strategic changes, then it invariably enters into a new regime characterized by a lack of data from the relevant target distribution. So in this situation, the organization could try to leverage data from one or several source distributions that are not too dissimilar from the target distribution. So let me give you a few examples. So the retailer who has no demand data for France may leverage data from other countries, such as Spain and Germany, that are perhaps believed to have a similar customer structure. Similarly, a manufacturer who introduces for the very first time a smartwatch may leverage sales data for related existing products, such as classical smartphones or traditional watches. In addition, an investor trading in new securities with an unknown demand distribution may have access to return data from existing securities that were issued by similar companies. Okay, so let us revisit now our data-driven decision-making pipeline in view of what I've just discussed. So besides the target distribution, which appears in the stochastic program, this is the one that we really care about, we now also consider multiple source distributions that are different from, but hopefully similar to the target distribution. And much like the target distribution, the source distribution is also unobservable. However, we may have access to training data sets from all source distributions. And as usual, these training data sets can then be used to construct empirical distributions, in fact, a different empirical distribution for each of the source distributions. And these empirical distributions can then be passed to some method of data-driven optimization, which outputs an optimal decision. And the performance of this decision is then, as usual, assessed on a testing data set, which is sampled from the target distribution. Target distribution is really the one we care about. We care about the performance on the target distribution. Okay, so the goal of this talk is to propose a new DRO model for data-driven decision-making that makes use of multiple data sources. So one could simply set up a classical DRO model with a Wasserstein ambiguity set, of course. And however, there is a problem with that. So throughout the talk, we will assume that we have no or only very few samples from the target distribution, but relatively many samples from the source distributions. And in this situation, it's not clear how we should define the nominal distribution at the center of this Wasserstein ball. So there are different alternatives. One could define the nominal distribution simply as the empirical distribution of the samples from the target distribution. But of course, we have only very few of those, or maybe none, then this wouldn't even be possible. Alternatively, one could use the training samples from one of the source distributions to construct an empirical distribution that we put at the center of the ball. There are other possibilities. One could also actually pool the data and construct the empirical distribution on all samples from all distributions together. Or, and that's something I would like to discuss in more detail later, we could construct some sort of a barycenter of the empirical source distributions. In particular, one could construct a so-called Wasserstein barycenter. So to explain this in more detail, let me recall some basic definitions and results about Wasserstein barycenters. So assume first that we are given k different points in d-dimensional space, and assume that each of these points is assigned a non-negative weight. Let's assume the weights add up to 1. So the classical barycenter of these k points is then defined as the sum of the points multiplied by their weights. Simple as that. Now, equivalently, the barycenter can also be defined as a unique solution of a quadratic program that minimizes the weighted squared distances from the k points. And the two definitions are in fact equivalent, and this can be verified by just inspecting the first order optimality conditions of this convex quadratic program here. Now, the second definition, the one in terms of the optimization problem, can readily be extended from k-weighted points in RD to k-weighted probability distributions on RD. So what used to be the squared Euclidean distances between points in RD, which appear in the objective function of the quadratic program, they can simply be replaced by the squared, say, 2 Wasserstein distances between the distributions on RD. So this results in an optimization problem over distributions. And if it has a solution, this solution is called the 2 Wasserstein barycenter of the given input distributions. Another possibility would be to replace the squared 2 Wasserstein distances here by p Wasserstein distances raised to the pth power. And then the solution of the optimization problem is called the p Wasserstein barycenter. So this is just a very natural generalization of the notion of the barycenter from points in RD to distributions, which are points in the space of distributions. Okay, so Wasserstein barycenters are routinely used in computer graphics. The picture that's shown here.
Sorry, Daniel, there is a question about the previous slide.
Yes.
Which is what would happen if k goes to infinity?
So I suppose, so we didn't look into this limit because for us, the k is the number of source distributions to which we have access. And we didn't study a situation where we have a huge number of possible source distributions, but the idea was to use few. I assume you could, I mean, the classical barycenter of a probability distribution would be just integrating, I mean, this should be an integral, right, over the a distribution on the space with the weights, right? So I suppose in the classical case, this is easy. In the case of the distributions, you would have to first define some sigma algebra on the space of distributions, probably equipped with the Wasserstein metric. Then you can define Borel measures and so on. You can probably define an integral. So I assume this could be done if you're a mathematician, but we didn't look into it. So sorry, I can't say much more about this. Yeah, any other questions?
Not at the moment.
Okay, great. So as I was saying, Wasserstein barycenters are used in computer graphics. And here I show you a picture which I borrowed from Justin Solomon and co-authors. So this visualizes different 2 Wasserstein barycenters between 3 uniform distributions. That is the uniform distribution on a donut, the uniform distribution on a duck, and the uniform distribution on a cow. And what you see is, you see how these 2 Wasserstein barycenters actually change when you change the weights of the 3 distributions. So one could say that if you increase the weight that you assign to the cow, then your Wasserstein barycenter starts to look more and more like a cow. So Wasserstein barycenters also provide a natural and elegant method to aggregate different source distributions. And to see this, let's first look at a very simple stylized example. So let's assume we are given k univariate normal distributions. Let's assume they have different means, but they have all the same variance. Assume also that each source distribution is assigned a non-negative weight, lambda k, and the weights add up to 1. So to aggregate these k source distributions, one could simply calculate their mixture. And this is just the convex combination of the source distributions where the convex weight of the ith distribution is set to lambda I. Alternatively, one could calculate their Wasserstein barycenter using the weights here in the optimization problem. So the resulting aggregate distributions have actually radically different shapes. The mixture is no longer a Gaussian distribution, it's a multimodal distribution, while the Wasserstein barycenter actually remains unimodal and it remains even Gaussian. Now, both the mixture and the Wasserstein barycenter have the same mean. So in that respect, they are not different. And the mean of the aggregate distribution in both cases is just a convex combination of the means of the source distributions. However, the variance of the Wasserstein barycenter is equal to sigma squared. So that's the variance of each of the source distributions. It's the same one. And the variance of the mixture is actually strictly larger. So to see that this is strictly larger is, you can just use Jensen's inequality and this will immediately follow. So the more different the means of the source distributions are, the higher the variance of the mixture. So as the source distributions are supposed to capture stylized features of the target distribution, which we don't know, and because all source distributions are Gaussians and share the same variance sigma squared, it is probably reasonable to expect that the target distribution should be Gaussian and should have variance close to sigma squared. And from the table here, it thus seems that the two Wasserstein barycenter is the more plausible model for the target distribution than the mixture. So the video here shows actually the mixture in green and the two Wasserstein barycenter in gray of two univariate normal distributions visualized in blue and red as the relative weights of P1 and P2 are changed from 0 to 1 and back. So we've seen that Wasserstein barycenters have many attractive properties. Unfortunately, they also have several shortcomings. So first, the two Wasserstein barycenters, which are the most widely used ones, they turn out to be extremely sensitive to perturbations in the input, in the source distributions. And this is certainly troubling from the modeling perspective. So if you just slightly change or misestimate your source distribution, then this could have a dramatic impact on your barycenter. In addition, we have been able to show that the empirical two Wasserstein barycenter is biased. So to see this, assume that we want to compute the barycenter, denoted by P star, of K source distributions. However, let's assume that we only have access to empirical distributions constructed from training samples, so from these source distributions. And that means we cannot compute the exact Wasserstein barycenter, but we have to find an estimator. Now, a very natural estimator would be the Wasserstein barycenter P hat of the K empirical source distributions. So this is an estimator for P star. And however, this turns out to be a biased estimator. So the expected variance of the empirical barycenter P hat is smaller than the variance of the true Wasserstein barycenter P star. And the inequality turns out to be strict if the source distributions are continuous. And here by the variance of a multivariate distribution, we mean actually the trace of its covariance matrix. And also, I should point out that the expectation here is evaluated with respect to the training samples of all the empirical distributions. Okay, finally, I would like to say something about one Wasserstein barycenter. So the one Wasserstein distance is widely used in DRO. And it's easy to see that the one Wasserstein barycenters of two source distributions coincides actually with one of the two source distribution, whichever is assigned the higher weight. So the barycenter is just one of the two distributions. This is, of course, not very interesting, right? That would tell us if we work with the barycenter, just use one data set and throw the other one away. So this is not very useful in practice. So let's go back now to our Wasserstein DRO model for decision-making with multiple data sources. So assuming we formulate this as a problem with a Wasserstein ambiguity set, and we have to decide what distribution to put into the center of the ball. So if we set the nominal distribution to the empirical target distribution, then the solution of this DRO model is likely to have an extremely high variance. The reason being that we assume that we only have access to very few target samples. So that's probably not a good approach. If we set a nominal distribution to one of the empirical source distributions, then the solution of the DRO problem will have a high bias. Actually, if we set the nominal distribution to a mixture of the empirical source distributions, then the solution will also have a high bias. For one reason for this is that mixtures miss important stylized features of the source distributions, as we've seen in our example. Another reason is that, of course, if we pool the data sets and we have only few target data, but many source data points, then the source data completely dominates target data and the bias persists. So if we set as a fourth possibility the nominal distribution to a Wasserstein barycenter of the empirical source distributions, then the solution of the DRO problem will potentially inherit the problems of Wasserstein barycenters we have just seen, which are sensitivity to perturbations and all sorts of biases. So in view of these challenges, we propose a new approach to data-driven decision-making with multiple data sources, and we call this multi-source DRO. So recall that any useful source distribution, pk, must be somehow close to the target distribution p. And therefore, it's reasonable to assume that the decision maker has a belief about this discrepancy between p, the unknown target distribution, and pk, some known source distribution. Let's say the proximity here is with respect to some Wasserstein distance. So it's reasonable to assume that the decision maker has some belief about this Wasserstein distance. Now, as the empirical source distribution p hat k approximates pk, any such belief naturally translates into an upper bound on the Wasserstein distance between the target distribution p and the empirical source distribution p hat k. So this would imply that p resides in a Wasserstein ball around the empirical source distribution p hat k. But this is true for every k. So therefore, p should actually reside in the intersection of k Wasserstein balls, one for each of the data sources. So multi-source DRO models are therefore models whose ambiguity sets are obtained by intersecting multiple Wasserstein balls associated with different data sources. So actually, special instances of multi-source DRO with k equals 2 source distributions have already been studied in special contexts. For example, they've been studied in the context of linear regression and logistic regression. And I should also point out that intersections of different ambiguity sets, 2 different ambiguity sets, in fact, have also recently been proposed as a means to mitigate the conservativeness of some simpler DRO models. Okay. So now I would like to give you an idea on how we could solve multi-source DRO problems. And to do so, I will actually focus on sort of nature's subproblem, which aims to find the worst case distribution in the intersection of k Wasserstein balls. So this problem maximizes over all distributions in RD that have a distance of at most epsilon k, radius of the ball, right, from the empirical source distribution p hat k. So in here, actually, I will assume that the distance between p and p hat k is measured by a general optimal transport discrepancy, of which any Wasserstein distance is, in fact, a special case. So the optimal transport discrepancy is defined as the optimal value of an optimal transport problem, which minimizes the expected value, the integral, of a cost function c over all transportation plans pi k. So here pi k, the transportation plan, is a joint distribution of the random variable vectors xi and xi hat k, under which xi has marginal distribution p, and xi hat k has marginal distribution p hat k. Okay, so we can thus actually replace this optimal transport discrepancy in the optimization problem with its definition. And because this distance appears on the left-hand side of a less than or equal inequality, we can just drop the minimization operator. To make up for this, however, we need to introduce the transportation plan pi k as an additional auxiliary decision variable in our problem. Okay, so now note that there is a different transportation plan for each source distribution p hat k. So the first transportation plan couples xi with xi hat 1. The second one couples xi with xi hat 2. The third one xi with xi hat 3, and so on, right? So an iterative application of the well-known gluing lemma from the optimal transport theory then shows that there must exist a so-called multi-margin transportation plan pi, which combines these standard transportation plans. So pi is a joint distribution of xi, xi hat 1, xi hat 2, xi hat 3, and so on, under which the marginal distribution of xi and xi hat k together, the marginal distribution of this pair, coincides with the transportation plan pi k. Now, this multi-marginal transportation plan can also be treated as a new auxiliary decision variable of nature's subproblem. So we can include it here, right? But if we do that, and if we ensure that the marginal distributions of xi and the xi hat k under pi coincide with p and p hat k for every k, respectively, then we can actually also eliminate the original transportation plans pi k, and they're actually no longer needed in this problem. So we can just eliminate them and replace them by the multi-margin transportation plan. So here's a visualization of a multi-margin transportation plan pi. And this is shown in a situation when there are two empirical source distributions with 3 training samples each. So pi is a joint distribution of the random variables xi, xi hat 1 and xi hat 2, which have respective marginal distributions p hat 1 and p hat 2. Note that p hat 1 and p hat 2 are uniform empirical distributions on the underlying training samples. So the picture shows that the multi-margin transportation plan pi actually decomposes into several non-negative Borel measures, which are visualized in blue. So each of these Borel measures corresponds to a training sample from p hat 1 and a training sample from p hat 2. Therefore, it has 2 indices. For example, the measure nu23, shown here, corresponds to the second training sample from p hat 1 and to the third training sample from p hat 2. In general, we assign each of these Borel measures a multi-index alpha. So this has as many components as you have source distributions, and each component refers to the sample from the respective, the number of the sample of the respective source distribution. So each Borel measure, nu alpha, then represents a distribution of xi, conditional on a particular realization of xi hat k for each k, multiplied by the joint probability of these realizations. So in summary, pi can therefore be expressed as a sum of the nu alphas times delta alphas over all multi-indices alpha. And here the delta alpha just represents the Dirac distribution of the training samples corresponding to the multi-index alpha. Okay, so now let's go back to nature's subproblem. And let's just replace the multi-margin transportation plan pi by its decomposition into Borel measures nu alpha that we derived on the last slide. And at this point, I no longer expect you to follow all the details. You don't need to parse this solution. What matters at this point is now we have reduced the problem to a semi-infinite linear program with finitely many constraints and infinitely many decision variables, because these nu alpha range over infinite dimensional spaces of measures. And of course, we know how to deal with such problems in DRO. We can construct the corresponding dual problem, which is also a semi-infinite linear program. And this one has finitely many dual decision variables, but infinitely many constraints, which are parameterized by the realizations of the random vector xi. So now we can use standard tools from robust optimization to handle such problems. So in particular, we can prove that nature's subproblem can be reformulated as a finite convex program if the transportation cost function C is convex in its first argument, and if the loss function L is piecewise concave in xi. I should point out at this point, however, that this convex program has decision variables and constraints for each multi-index alpha. Now, if each of the k empirical source distributions has n samples, then this means that our convex program has of the order n to the power k many decision variables and constraints. So therefore, the problem size grows exponentially with the number of source distributions, with k, right? Accordingly, it's perhaps not surprising that we can prove that the problem is NP-hard, even if the transportation cost function is convex quadratic. So a very simple situation. And even if the loss function vanishes, is identically 0. So the proof of this hardness result is actually based on a reduction of nature's subproblem from the NP-hard two Wasserstein barycenter problem. So this has been shown to be NP-hard by Altschuler and Boazera in 2021. So perhaps surprisingly, however, we can also prove that if the transportation cost function grows faster than the loss function, then nature's subproblem has an optimal solution, and it is solved by a discrete distribution with only 1 plus n times k atoms. So this is good news, right? Because it says that the solution of this NP-hard problem can at least be written in time polynomial, in fact linear in k, the number of source distributions. So this encourages us to look for efficient solution algorithms when some problem dimensions are fixed. And to do so, recall that nature's subproblem has actually many robust constraints, right? So I just repeat these robust constraints here. And there is one for each multi-index alpha. And you remember that these are n to the power k many multi-indices. We'll now show that many of these robust constraints are in fact redundant and can be eliminated. So to see this, let's first combine all of these robust constraints to a single robust constraint by just maximizing the constraint function over alpha. Now we only need to maintain alphas here for which there exists at least one psi for which this particular alpha maximizes this function, right? If a particular alpha never attains the maximum here, then this particular alpha is irrelevant and can actually be eliminated. So this is what we try to do. We'll try to reduce the set, this set which has exponentially many indices, and we try to reduce it, right? By eliminating unnecessary constraints. So if we want to maximize this function here over alpha, note that the kth component of alpha appears just here, right? So instead of maximizing here over alpha, we can actually inside, because of the minus side, we can actually minimize inside here just over the kth component of the multi-index, right? We can minimize here, and we can ask for which scenarios psi is the kth, is the particular value of the index alpha k optimal in this minimization problem. So to visualize that, we can actually visualize this as a partition of the space of the uncertain realizations psi, right? So each index alpha k, and there are n of those, leads to a cell in this space, and this is the cell of psi's for which this particular alpha minimizes this expression. Now, of course, we have to do the same thing for every source distribution, right? And we have k of those. So in the example, I plot k equals 3. So each term in the sum here leads to a different partition of the psi space, telling us for which scenarios the index alpha k attains the minimum here for a different k, right? Now, of course, we are interested in knowing when a particular multi-index, which has multiple components, is optimal. So we should actually, what we should do is we should intersect these partitions, which leads to a refined partition shown at the bottom here. And this refined partition contains a cell for each multi-index alpha. So therefore, while these partitions contain each n cells, this one in principle contains n to the power k cells. Okay. Now it turns out, however, that many of these cells are empty. And we denote by A prime here the subset of multi-indices for which the corresponding cell, C alpha here, is not empty. So in our robust constraint, instead of maximizing over all multi-indices in A, it's actually sufficient to only optimize over those in A prime, the reduced index set. A very interesting result by Altschuler and Boazera states that if the dimension D of the uncertainty is kept fixed, then the index set A prime of all non-empty cells can be constructed in time polynomial in n and k. And actually, they discovered this result when studying efficient algorithms for computing Wasserstein barycenters. So this is very closely related to their problem. So using this result, we can prove the following main theorem. So if standard convexity conditions hold, then the optimal value of nature's subproblem can be computed to any accuracy delta with the ellipsoid algorithm. And in fact, there are two different versions of the ellipsoid method. The first one runs in time polynomial in n, d, and log 1 over delta, the accuracy, with an exponential dependence on the number k of source distributions. And the second one runs in time polynomial in n, k, and log 1 over delta, with an exponential dependence on the dimension d of psi. So whatever variable you want to increase, as long as you keep the other one fixed, So either keeping the number of source distributions small or the dimension small, you can solve the problem in polynomial time. Okay, so now now that we know how to solve multi-source TRO problems, or at least nature's subproblem, we should also investigate our statistical properties. So we want to ensure that the optimal value of a multi-source TRO problem provides an upper confidence bound on the corresponding stochastic program under the unknown target distribution P. And for this purpose, we have developed a Bayesian measure concentration result, which ensures that P belongs to any of the K Wasserstein balls with high confidence. So we assume here that the first source distribution P1 is actually equal to the target distribution, because we want to see also what happens when we have some target samples. And we prove that actually P1, the target distribution, belongs to the kth Wasserstein ball with a probability 1 minus beta fk. Okay, so that's on a high level, that's the statement. So let me tell you what everything means. So this is a Bayesian result. That means the probability is not only evaluated with respect to the distributions of the training samples, but also with respect to our beliefs about the source distributions pk. Okay. Now, the probability is, of course, not evaluated with respect to our prior beliefs, but with respect to our posterior beliefs after observing the empirical Wasserstein distance. So basically the Wasserstein distance between the empirical target distribution P at 1 and the empirical source distribution P at k. And so our significance level beta k here, this is a Bayesian significance level, which drops to 0 as the radius epsilon k of this ball goes to infinity. It is a function of the number n1 of samples from the target distribution and number nk of samples from the kth source distribution. And it depends on parametrically on our belief about the distance between the target distribution P1 and the source distribution Pk. So this Fk is just the CDF of this distance. This is our prior belief. So we actually develop an explicit formula for this significance level beta Fk, but I do not show it here because it involves many integrals. It's a complicated formula. But what matters is maybe the plot here. So it visualizes the normalized Bayesian significance level beta Fk as a function of the normalized Wasserstein radius epsilon k. And as expected, the radius, as the radius grows, the significance level beta Fk drops quickly to 0. Now, the speed of decay depends on the quality of the prior belief distribution Fk. The stronger the prior, the faster the decay. A prior is strong if it concentrates probability mass close to the true unknown Wasserstein distance between P1 and Pk, right? So in the limit of an extremely weak prior, or if there's no prior, then we can prove that our result just recovers the frequentist measure concentration result due to Fournier and Guillen, which is widely used in the literature. So let me now show you some numerical results. So let me first look at a mean CVAR portfolio selection problem involving 10 assets. And our first experiment is based on synthetic data. So specifically, we assume that the return xi I of the ith asset can be expressed as the sum of a systematic risk factor psi, which is common to all assets, and an idiosyncratic risk factor zeta I, which is independent across the assets. So that's how we generate the data, right? And that's the true target. That describes basically the target distribution, kind of. So all risk factors follow normal distributions. Now, under the target distribution, P1, right? The means, so these RIs, of the first 2 assets are positive, and the remaining 8 assets have negative means. In contrast, under the source distribution P2 here, the means are positive for the first 5 assets and negative for the rest. Okay, so that's how we generate one target and one source distribution. Now, we assume that the investor has access to only 5 samples from the target distribution, but to 30 samples from the source distribution. The table here shows out-of-sample Sharpe ratios, expected values, and standard deviations of the optimal portfolios obtained with different DRO schemes. So this is, we compare multi-source DRO, here, this is our method, against single-source DRO. So this is basically DRO with one single Wasserstein ball. for different nominal distributions. So we use as nominal distributions in single source TRO just the empirical distribution on the target, or the source data, or the empirical distribution on the pooled data, or the empirical distribution which corresponds to some Wasserstein barycenter. So the results show that as target data is scarce, using the source data actually helps, right? So using target data alone performs poorly and is dominated by other methods. And in fact, multi-source TRO performs particularly well, and it largely dominates single-source TRO. It attains the highest Sharpe ratio and the highest mean. It does not win in terms of standard deviation, but this should actually not be expected because given the data here, one can show that the uniform, the portfolio that the equally weighted portfolio must actually minimize the variance. And it's of course, sorry, the portfolio. Sorry, yeah, that's what I want to say. So basically, we should not expect the variance to be high, to be low. So the second experiment is based on real sector data from the Morgan Stanley Capital International MSCI online database. And so here we collected data for Europe, the US, and the Pacific region. So this was industry sector data for these three regions. So we then assume that an investor seeks a portfolio for a target region based on few samples from the target region and abundant samples from one source region. So the table shows that the multi-source TRO generally attains the highest Sharpe ratios, unless the target region has a rather different economy than the source region. So that happens here, right, where the target is the Pacific region and the data we have is from Europe. So here, multi-source TRO doesn't help very much. So the European data doesn't help much because the Pacific is very different. The same happens down here if we want to predict the Pacific region, but we have only data from the US. So then other methods win. In all other cases, actually, multi-source TRO performs better. So I should say that in this example, we assume to have access to 30 samples from the source distribution. And from the target distribution, we increase the sample size from 5 to 50. Sorry, we had 50 samples in the source distribution. So let us look at one last example, which is an assortment optimization problem based on data from Kaggle. And the decision maker here must select a subset of at most 3 out of 10 products to be offered in a new store, say the store in France, right? And there's demand data for the country of the new store, but also for 2 different countries. And the marginal demand distributions of the 10 products in the 3 countries based on data are just visualized here at the bottom. So we also compared multi-source TRO against different versions of single-source TRO with one single Wasserstein ball. And again, we see that multi-source TRO actually dominates various single-source TRO schemes in terms of auto-sample expected revenue. So this shows again that actually, if there is source data available from countries that are similar to the country you're interested in, then it is beneficial to actually make use of that data. And multi-source TRO is a method that seems promising to leverage this data. So this brings me to the end. Here's a brief summary of my talk. So we have introduced multi-source TRO as a tool for data-driven optimization when we have access to multiple data sources. It is actually reminiscent of domain adaptation and transfer learning and machine learning. Now, our proposed approach to multi-source TRO is dually related to the computation of Wasserstein barycenters. And we have then shown that nature's subproblem is a huge convex program with exponentially many variables and constraints. So n to the power of k. K is the number of source distributions and n is the number of samples per source distribution. Accordingly, this problem is NP-hard, even though it's a convex program. However, it is solved by a discrete distribution with at most 1 plus n times k atoms. So we have shown that this problem is tractable if either the dimension d or the number of source distributions k is fixed. We have also derived a Bayesian measure concentration result that can be used to obtain auto-sample performance guarantees. And we have shown numerically that source data can be very useful when there is reason to believe that it comes from a distribution that is close to the target distribution. So this is the end of my talk. The paper I presented is available on archive through this QR code here, and I should credit again my fantastic co-authors. Thank you very much for attention, and be happy to look forward to the discussion.